Hello everyone and welcome to a new video where today we'll be taking a look at Brane, someone that I've actually not looked at, even though he seems to be one of the bigger flat earthers, where Brane seems to have an issue because the oblate spheroid concept can't work apparently. I'm certainly keen to hear that. Now Brane, I don't think we've had the honors yet. I'm Olaf from Olaf Does Astro. I currently doing my master's degree in astronomy and physics, and I can assure you, even though I've not watched your video as a whole previously, I've only watched like the first minute to figure out if it's worth doing a video about. I can assure you, your opinion there is rooted in nothing but misunderstanding. But I think this will come obvious to the average observer very quickly. So let's have a go, shall we?
My friends, you are gonna love this.
Although I laugh, I find the laugh there very funny though.
This is gonna debunk the spinning ball.
I can't wait. Because the usual flat earth recipe is, right, the flat earth recipe of choice is misunderstand something about the actual model that we use, show an observation or misinterpret that factoid or law of physics or something like that, and then say that, see, your model can't work. Well, because in order to disprove a model sufficiently, you need to have at least some rudimentary understanding of the model.
Not only going to debunk the spheroid, but it's also going to debunk the entire ball, because you'll see. They say we live on a rotating sphere with 1,000 mile per hour rotational speed at the equator.
And first thing, rotational speed is not measured. We talked about this in the last video. Rotational speed is not measured, importantly, in linear velocity, like meters per second or miles per hour or something like that. It urgently needs to be measured in angular velocity, like rotations per minute or radians per second or degrees per hour, something like that, right? So already kind of non-favorable here.
And as you go up 10 degrees from the equator, let's say up toward the North Pole, it drops to 900 miles per hour. And you go up and up.
No, you go up 9 degrees and it will drop by that. You are aware, please tell me that you know that the equator is at 90 degrees. From the poles, depends on where you define it. You can define the equator as 0. The poles would be at 90, you could define the poles at 0 and then the equator would be at 90. So you go up not 10 degrees to drop 100 miles per hour. You go 9 because you need, right? You get that. So 30 seconds in already being a bit wrong here.
Another 10 and it's 800.
Although it's not important really.
100 miles per hour. And another 10 it's 700, so forth, all the way up to the North Pole where it's essentially not even moving, right? And so they say there's a 14-mile high bulge. That's twice the height of a commercial airliner.
Yeah, I wouldn't call it a bulge. I mean, it's not wrong, right? It's just that due to the rotation, as you say correctly in the slide here, the rock, the stuff that the Earth is made of, just gets during the formation of Earth, really, or in the earlier stages, just got a bit reshaped from a sphere into a rotating ellipsoid, but this change is very, 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 very small. Don't forget that. I don't do in miles. You know, I'm from Europe, or from anywhere outside the US. It's really 22.5 kilometers, right? Now the Earth has a radius of 6,371 kilometers, so this is very, very, very little. This is less than a percent, less than 0.5% even, right? It's tiny, this change. Tiny, absolutely minuscule.
This is rock and dirt and everything it would be.
Well, yeah, back then when the bulge, I'm calling it a bulge now as well, just for the sake of clarity here. When it formed, as far as I'm aware, or like during in the process of forming, there wasn't much dirt around. It was mostly rock, you know.
Everything. I'll get to that in a minute. It would be everything. You know, clouds, air particles.
It would certainly not be everything. Why would you reach this conclusion? the force exerted on things based on Earth's rotation is absolutely tiny, sitting at around 2.5 or something centimeters per second squared. That's very, very little. And of course, it is enough for rock, because rock isn't really, subject to any much other force, especially not in bulk, right? The bulk rock that makes up the Earth isn't really subject to any other force than, that, right? Gravity and the rotational force. Clouds, however, are affected by winds. They are affected by the macroclimate.
And a lot more. Okay, it would all shift, and the poles are essentially just collapsing.
I would be fascinated to see your calculations for why everything would go to the equator.
They're just filling the void, right? So the ground that was shifting and moving, piling up 14 miles high, is packed, right? It's packed up with dirt. And so here's the big takeaway from this. The fact that the ground has stopped moving, yet the rotation is still going. So the ground has filled in as it's all moved toward the equator, and it reaches a point and it stops. It's packed up, it's filled in all the voids, right? It's filled in.
I wouldn't call it void. It's a continuous deformation from a sphere to an oblate spheroid.
And this is where they'll say, well, that's why we're in equilibrium, Wayne. Well, no.
Yeah, we are in equilibrium. I mean, depends what you mean with we, right? But overall, the bulk mass of Earth is certainly in equilibrium.
Because nothing has changed for us. The rotation that has caused the ground right below our feet to...
We weren't around back when the bulge was established. What are you saying? That this happened like yesterday? This happened like way early in the stage of planet formation. That's like, we're talking several millions or billions maybe even. Yeah, let me have a quick something like that around, right? So that's very long ago.
Move and shift and to the equator and pile up 14 miles high is still going. This shows you right here, this is a complete fraud, a complete utter joke. Neil deGrasse and his spheroid, complete joke. The rotation is said to be sustaining and holding this in place because...
Well, there's now an additional force acting upon the rock, right? The centrifugal force from the rotation. And the best configuration, the lowest energy configuration, because that's what nature does, it always seeks to go into the lowest energy configuration, just is this oblate spheroid.
To their own admission, they say when the Earth rotated faster, the bulge was bigger. Now that it's...
Yeah, if the Earth rotated faster, the bulge would be... bulge again, the oblateness would be higher, yes.
Down a little, the bulge receded. It's a little smaller. They're shooting themselves in the foot with this one. I love it. Thank you, Neil deGrasse Tyson, for reinforcing this nonsense. So, again, the ground below us, the only reason it stopped moving is because it's piled up, and it stopped.
It's in equilibrium, yes. Well done. Newton's first law, an object in motion will stay in motion unless acted upon by force. And in this case, we have the constant motion of velocity 0, right? So it's stationary. And the forces that are acting upon it are in equilibrium. That is, the force of gravity pushing the rock down, and the force from the elasticity and compression modules, it's what they call in solid state physics, or like material physics, the force from the compression module, because the stone is being compressed, it exerts a force in the other direction from which it is compressed from, kind of, and those two are in balance, or else the ground would move substantially. Of course, it moves comparatively small due to things like erosion and things like that, but that's not really a kinematic reason, that's like a geological or almost meteorological reason.
At this speed, that's as high as the bulge will get, and that's as far as the ground will slide.
Yeah, that's its equilibrium stage for this set amount of centrifugal force, yes.
Down, as per Newton's law, an object in motion will tend to stay in motion at a constant speed and in a straight line. And remember, everywhere on a sphere, on a rotating sphere, except for the equator, everywhere else, all the other latitude lines, is a turn. And the turn gets more severe as you go.
Yes, the latitude lines are not in the spherical geometrical sense straight, yes.
Go toward the North Pole. The speed slows down, but the turn becomes greater. So you have water and everything wants to go in a straight line. Us people would want to go in a straight line. This is what we would look like.
It's not what we would look like. Jesus Christ. My dude. Okay. The force of Earth's rotation, the centrifugal force from Earth's rotation, is tiny. It's so small. We discovered that. We discussed it last week. The force or the acceleration that you would notice, or that you do notice, is so tiny. It's like going from a car, like with a car, from 0 to 60 in like 20 or something, 21 I believe it was, minutes. That's how tiny it is. Absolutely tiny. And hear me out, and that might sound crazy, humans have a way of moving. Oh, well, rocks don't. I can't believe I have to explain this to grown-up. When a rock, let's make it the simplest possible example I can come up with, right? Let's say a rock breaks. And there's a tiny force towards one direction. More of the particles of the rock breaking will move to that one direction, even if the force is tiny. Now, this in order for that to form an oblate spheroid, this takes many. I assume that's a bit off the cuff now. I assume this would take many millions of years until the rock has found its way into the lowest equilibrium stage, right? Humans or tumbleweeds or planes or whatever you have another way of moving. It's really not difficult for a human to overcome this tiny acceleration. And I know that you say that it doesn't exist. I have in my last video linked the source where you can see that scales actually give off a lower measurement for weight near the equator due to this centrifugal acceleration.
Get relief, get alignment, get good
posture.
posture.
Come on.
This
I've
is
never
the
had an ad in one of my videos. Go away.
We would look like
Sorry
tumbleweeds on a windy day out in the Nevada.
We would not. I will, after the initial reaction, have a bit of maths for you at the end. I hope you're not one of the flat earthers who is scared of numbers, where I will show the difference in acceleration between, for example, a tumbleweed caught in the wind and other things.
Out of desert, we would all be blown. Everything would be flying towards the equator. We'd be.
Please, I beg you, please supply the math. I would be thrilled to go through it and have something to laugh about.
Piled up just like the ground is below us, and this is right now. They say this is right now. The Earth is spinning at 1,000 miles per hour. This sphere.
We say the Earth is spinning about 15 degrees every hour, just so you know.
This is such a joke. It is so busted right now, and all these tumbleweeds would be.
He has said it's busted, and now it is absolutely busted. Can't have any arguments against it. He has decided it is, and therefore it is. Jesus Christ.
Akin to being.
How did I not come about him sooner? He's a prime example of thinking you know everything better than everyone else in the world. I love it.
Stacked up at the equator, right? From both north and south, people, everything on the Earth.
Again, please supply the math. I can't wait.
Earth would move. Don't believe that? Well, I'll try to convince you with this. There's a spinning warp.
Okay, so let's take something that spins with many total rotations a minute and compare it to something that rotates like once a day. I will love to go through the acceleration that would be felt on the surface of the right ball here. Is this really? Are you really that dense that you're using the old the water would fly off argument? I can't believe it. Wow. And it's like 7 months ago. That's not an old video. Jesus.
And a spinning, soaked, porous rubber ball. So the water can freely fly off of this ball. The balloon is holding in the water, of course, right? But it's bulging. Now, this would be akin to the ground on the Earth. It's bulging.
Hey, that's correct. I mean, it's rotating way too fast. That change here is so huge. You would need less than 0.5% of change from the radius of the object to the actual magnitude of the bulge. Less than 0.5%. That's not less than 0.5%. That's like 50 or 60 or 70% or something like that.
But it's not falling apart. It's just bulging and flattening. We would be the water and everything on the Earth, right? So as this starts to spin and bulge, once it started to bulge, it's already way past the water flying off. We're all doomed.
No. The effect is so small. Now we can compare it suitably to gravity, right? So we have 9.81 meters per second squared of acceleration pointing downwards. and we have 2 centimeters. That's a centimeter is 100th of a meter pointing up. Wow. I can't make it up. That's about like 2 per mil, not percent, 2 per mil of the gravity force is actually acting up due to the centrifugal acceleration. But I will detail this in the calculations that will follow this initial reaction.
This is just to show you what a hoax this is. That if you have water on the outside of this balloon, it's long gone. Before it even bulges, as you can see, just as I start rotating the rubber ball, the porous rubber ball on the right, the water starts to fly off immediately. Right there, it's gone. It didn't even get up to speed yet.
My dudes, your this comparison is so ridiculous. It's like me. I have a bag of peanuts right next to me. Right, I eat peanuts while I work. It's like me taking one of these peanuts and shooting it at the wall, and then showing that, well, the peanut didn't penetrate the wall. So how should something ever destroy a tank? Because nothing can penetrate it. Clearly, that's what you're doing. The scale of this is so completely off. We are talking many orders of magnitude here. But I will calculate that for you later. You don't worry. You don't need to actually use your brain. But yeah, you'll see.
But it doesn't matter. The balloon is going way faster, but yet it has a skin to hold in the water, right? And the reason it moves to the equator, as I've said, is the Earth wants to turn left out from under it. As per Newton's first law of motion, the law of inertia, everything wants to move in a straight line, wants to stay in a straight line. So as the Earth turns, that's why you would theoretically have this equatorial bulge. But it's not real. But if you did, again, the ground is currently spinning right now underneath us, but the ground is done moving, kind of like this water balloon.
What do you mean the ground is done moving? It's still rotating with us, of course. I understand that, but that you mean it's not bulging any more or less, so like the size of the bulge isn't changing. But yeah, so what? The acceleration imparted on a human would still be tiny.
Is stacked up inside there, it's pressing against the walls, and it's done moving. From both poles of the water balloon, it's moved into the center, and it's not going any further. You could just have a steady rotation there. But the stuff that's free to move on the outside of the ball that lives on this balloon is gone. You understand? We cannot be rotating, sustaining, the ground sustaining this huge bulge, 14 miles high, and the poles flattening, and us on the surface not experience. Don't you see? This is physically impossible.
Hi, I am currently doing my master's degree in physics. I assure you it's not, and I also assure you have no idea what you're talking about. So no, it's not physically impossible. But again, the numbers will follow.
This is not a reality. It can't be. It's fake. That's all. Let's go on. The hardest thing I've had to do is try to explain this.
Go on about what? You've talked about the same point for 6 minutes now. That could have easily been done in like one video. But okay, sure.
And even get it straight in my own head. It's been very hard. That's why I was...
I believe you that it's been very, very difficult to wrap your head around that, yes.
Silent for like almost 3 months. I didn't put a video out because I've been struggling with this. But when I got this, it's because the ground has stopped. Oh, but we are on the ground. We haven't piled up against each other. We're not...
And why should we? The force exerted on us is tiny, and we have another way of moving around. We can use our legs. We can even use our arms. To move around. And it's so easy for a human to impart an acceleration on oneself that's bigger than the centrifugal force.
All at the equator bunched up? We would have to be. All the water. Look at this, still water like a mirror. This is busted.
No, the water, because again, water also is primarily affected by kinematic factors such as gravity or the centrifugal acceleration. Water would also have this slight bulge, but it's so tiny, less than 0.5% of the Earth's radius. Less than 0.5%. Please think about it. It's tiny. On a lake that size, I don't know which lake it is, it looks very nice. On a lake that size, you wouldn't even barely notice such a bulge. If let's say this lake is 1 nautical mile, right? This would mean it would be 1/60th of a degree in curvature. How would you detect it? Do you have any device? Because what you're doing right now is you're looking at it and saying, well, that's not curved. How close do you think, or how well do you think your eyes can determine that something is curved or not? What's the margin of error there?
Oh, man. I hope you guys
Yeah, oh man, indeed.
get this. I imagine I'll keep putting videos out on this just because. So,
He hasn't. Gee God, I wonder why.
give this a thumbs up right now, please. And maybe I'll come up with more graphics and stuff like I normally do in videos. Give this a thumbs up right now. Share it with others. Watch it more than once. Come on back. It's a short video. I'm going to end it like right here. So that's it. What's the takeaway? Is that this bulge that they say is right now 14 miles high all around the equator, and the poles are squashing in. Again, the poles do nothing. They're just filling in the ground that's voiding, that's vacating out and moving up 14 miles high at the equator. All that ground has to shift. And so now it's stopped shifting, not because the Earth has stopped rotating, but because the ground is packed up against itself. And so it's stopped. So that's it. The fact that the ground has stopped, yet we're still on the ground, we're still on the rotating ball, the same rotating ball that moved all this rock and dirt and piled it up 14 miles high on the equator and shifted it from the poles all the way up to the equator. We're still on that ball. The same force that moved all that stuff is still here. Nothing's changed, except for the part where all the dirt and rock has reached its limit of movement as far as it can go, yet we're still under that same force that has done that and is sustaining that, yet we're to believe, and we're told, we're gaslighted into believing we're living on the surface, no problem. No, we would be stacked.
Again, please supply your numbers. I would be most curious about that. I think it's fair enough to end it on this notice with gaslighting. Yeah. So I will now go over to my trusted OneNote notebook to go very, very briefly with some of the numbers involved and show why your comparisons make absolutely no sense. So here we are, back at the old trusty OneNote notebook. Now you can see clearly here. But first of all, excuse me for how the OneNote notebook looks. It's a bit different on Ubuntu than it does on Windows, so that's why it looks a bit weird. Yeah. So rotation and pbrane. Let's begin. I find the name pbrane rather fitting. Because it sounds like he has a P for the brain. Let's not go there. So first of all, the centrifugal force is given by mass times the angular velocity squared times the radius, which is the same as mass times the tangential velocity squared divided by the radius, because velocity is the tangential velocity times the radius, the tangential velocity. And so since force is mass times acceleration, we can figure here that the acceleration is just the omega squared times r. Omega here is in SI units, which is radians per second. Now, once every 24 hours, which is the rotational speed of the Earth, is equal to about 7.3 times 10 to the minus 5 radians every second. When you square that and multiply it with Earth's radius, you get around 3.3 centimeters per second squared. I said in the earlier part around 2 point something. I want to apologize for that. That's the centrifugal acceleration I feel where I usually am in Europe. I calculated it for that position once, but it's the same magnitude. So all of the statements are still true. So this gives us a centrifugal acceleration at the equator of about 3.3 centimeters per second squared. Yeah. So let's look at the couple of cases that we have here, right? So with a rock, well, let's say that's not at the equator. There's a Q missing here. I don't know what happened to it. I'm sorry. Sometimes OneNote deletes random symbols. I don't know why it does that. So you have a rock. This is not to proportion, by the way. You have gravity weighing it down, and you have a small force that's less than 3.3 centimeters per second squared, because we're not at the equator. But thus, the force is also not pointing straight up. It's pointing slightly to the side. I drew it here only to the side so you would get my point. The fact is that the resulting force will not be straight down, but will be slightly off. And due to this being slightly off, again, when rocks undergo transformational events, when they melt and things like that, they will conform to the forces acting on them, thus creating the oblate spheroid that we know and live on. So yes, on average, over a long time, or depending on which mechanisms are involved, I'm not a geologist, I know somewhat little about geophysics, but still, over somewhat of a long time, the rock mass, the bulk mass will move. Great. Now, what's up with water? Well, I originally wanted to draw the vector lengths here in proportion, but it's not possible. I will show you why. You see those little squares in the background? So that's 1 square long. And in order for gravity to be proportional here, this would have to be 300 squares long. That's 15 squares, mind you. And it would have to be 300 squares long, so I'm afraid I won't be able to do it. So the water has a tiny force acting upon it compared to the gravitational force that keeps it down. So the conclusion here is that the water wouldn't fly off the Earth, clearly. What about the drills? And that's why I said earlier that you're comparing me throwing a peanut against the wall and wondering why it doesn't penetrate the wall to the statement that no tank could ever, for example, or artillery or any gun or weapon could ever pass through a wall, right? And why did I say that? Well, let's say we have a drill here. My drill that I have at home has about 2,000 RPM. So I'm going with that. Although that's not a particularly fast or good drill. It's just, your average, you need to screw something in drill. So I assume that corded drills will go like 3,000 or even more. And I assumed the rubber ball with a diameter of 5 centimeters. That's just a rough ballpark. Could be 2 and it would still hold true. So again, the angular velocity squared times radius is the centrifugal acceleration for 2,000 RPM. That's 4,000 pi every 60 seconds. That gives us about 210 radians a second. That's squared, since that's our omega squared, gives us 44,100 times the radius of the ball in meters, gives us about 1,100 meters per second squared. So, compared to a tiny force of a couple of centimeters per second squared at best for the surface tension that keeps the water on the ball with the rubber ball, right? This is so completely wrong. This here is a whopping, we have 3 centimeters, roughly 3 centimeters per second squared, and here we have over 1,100 meters per second squared. Do you now know why I say that this comparison is so funny to me? Because right, that's over 36,000 times more force acting on the water on your drill than it is with Earth's rotation. Yeah, big surprise, the water will fly off, duh. So, P-Brain, please try to wrap this around your head. You said it's difficult. It really shouldn't be. That we talk in physics class, right? In the first year, amongst the first couple of weeks, we talk about forces and how they apply, right? And a simple problem like this would not even fill 1 exercise hour. This is a matter of minutes. When you say it took you 3 months to wrap your head around it, I don't know what to say. Okay, so okay. Let's leave it at that. Thank you all very much for watching. If you enjoyed this video, maybe consider leaving a like. If you enjoyed it a lot, maybe considering subscribing. So yeah, until the next video, I really hope you have a nice time, and I will see you in the next one, hopefully. Goodbye!